Hello. I'm going to give you a quick overview what I'm going to be talking about within the next 60 minutes. I'll tell you how I came to that baby, actually. I'll give you an introduction into the grid. Then we'll dive into the wireless ambus protocol. So that's going to be a bit maybe boring, but I'll show a demo afterwards, so it's worthwhile staying here. Okay, let's go. In summer 2011, I was involved into a program of the Federal Institute of Energy in Switzerland, and I got attention of the wireless ambus protocol. Then I had to write the master thesis, so I decided to go for the wireless ambus protocol because I felt it might be not that adequate as it should be. So then in Christmas 2012, the German Federal Institute of Information Security published a report on exactly that protocol, independently of my research. And it got mentioned at the CCC, so the Chaos Computer Congress in Hamburg as well, as inadequate. I then spent some time digging through the European norm paperwork and was trying to get some practice within a lab and finished my ambus analysis in March, where also the German Federal Institute of Information Security finally titled the protocol as insufficient, and now we're here. So what's the smart grid? The smart grid basically consists of few domains. So we have the bulk generation domain, we have a transmission domain, we have a distribution domain, which the distribution system operator takes care of. We have, of course, the consumers, households, industries. And in smart grids, we also have distributed generation and storage, which is not considered for the bulk generation. Distributed generation and storage might also happen on the distribution level, so it's just the blueprint. The protocol I'm speaking of is basically used at the consumer side. So to make the grid smart, we'll need a special infrastructure which basically connects the consumer side to the distributed system operator. This is called the the metering infrastructure. They call it the advanced metering infrastructure if you also send commands to the meters and if you not just gather information from that meters. So we have the head end there. It's also sometimes referred to as the metering device management, MDM, not to be confused with the MDM in mobile device management. So the head end is basically collecting all the information. It's basically taking care of patch management, firmware updates, sending commands to meters. Meters actually send their information to collectors. These collectors are sometimes also referred to as gateway, router, multi-utility controller, MUC. And a meter may also work as a relay, or a meter might forward its information to a relay and the relay forwards it to the controller. So we have wireless ambus within that neighborhood area, network area. You might wonder how such a collector looks like. That's a special collector which is called a multi-utility controller, so it can interface with electricity meters, gas meters, water meters, heat meters. It's actually built to fit on a top hat rail. It's head end side, so the part where he's speaking to the head end is actually GPRS. There's a port for the antenna. There's another port for the antenna for the wireless ambus part. That device also has a web interface which you can connect to see what meters are connected. That's a picture of such a GUI which allows identification of all connected meters. You can enter keys for the meters and basically observe values. So that information is basically forwarded then to the head end, which takes then care about the billing process and so on. Then here an example of a meter. It has several interfaces actually. There's an optical interface on the front, so for local configuration. They have various interfaces. Basically, you can plug in a little print which either has a GPRS interface, a Zigbee interface, a wireless emboss interface. There are wired versions, there are serial versions of such interfaces, and such a electricity meter supports, of course, consumption value reading. Some support prepayment. So you're going to tell the meter how much energy a consumer can use until it shuts off. You could do different tariffs, so you have maybe night and day tariff. You could also remotely disconnect or connect the consumer. All the pics I show you, don't blame these vendors to be vulnerable. Okay, these are just examples, please. Okay, let's quickly go through the wireless amber standard. So, wireless ambers is actually grown up within the heating metering industries 20 years ago. It's used by 15 million devices, mainly around Europe. So you could use it for remote meter reading. You could also implement applications like drive-by meter reading. You could use it for maintenance and configuration. The protocol does basically follow the ISO OSI stack. They omitted few layers. Actually, we have a physical layer. There's a documentation, a European norm, which specifies the frequency bands, modulation. We have a data link layer, which is specified in the part 4 of that specification as well. And it specifies also a so-called extended link layer. And we have an application layer which is specified within the 3rd part of that standard. So at the physical layer we have different frequencies used. We have 868 megahertz, 434 megahertz, and 169 megahertz, whereby the 169 megahertz is used for transmission over long distance, so we're talking about 5 miles. The other frequencies are actually used within more narrow scope, so we were talking about 100 meters. There are different line codings. And if we have a look at the link layer, there's a frame header, which has actually has some cyclic redundancy checks, so receivers can figure whether some packets got kindly manipulated. The frame header does also take care of the device addressing. So if I send a packet, then the receiver needs to know who sent that packet actually. And it does also specify the rest of the protocol, so all the gray boxes. So I could, for example, send responses on requests. I could send commands, alerts and errors. And we do have a second part. So we have either that frames or we have that extended link layer, which you could implement basically your custom protocol on top. And that link layer provides encryption. If we have a look at such a frame block, then you will see the first byte is basically defining the length. We have a control byte. It indicates, hey, this is just a message fire and forget, so send, no response. It identifies the manufacturer, and it contains the device address. And here we get to the first issue. So it discloses its version information, it discloses what type of meter it is, and it discloses the vendor. So by the time we are aware of vulnerabilities within these devices, it's easily to identify those devices and to exploit them. Let's go to the next part of the protocol. We have the data headers. There are different headers, 3 actually. There's no header, a short header which indicates access numbers. So access numbers are used to tell different packets apart. So I send them the first message has access number 0, the second message has access number 1, and so on. It's also used to detect replayed packets. The data header does also indicate encryption. So I told you there's the extended link layer over here. That part could provide encryption, or we have encryption on the application layer, which is signaled within the data header. We also have long headers. These are used to build applications where we need repeaters. So if you have a meter and a repeater, then the meter basically broadcasts a packet with its own meter address. The bridge picks it up and forwards it, of course, with the bridge address, but appends the meter address. So that's the long header. So the header end knows then exactly what meter in the end actually sent the information. If we look at that data header, I told you 1 byte is the access number. Then we have a status field which could also indicate alerts. So if you trigger some fraud detection mechanisms in the meter, they will signal it with the alert and error byte, and you can then go and query more detailed information from the meter. Then we have the configuration field. That configuration field actually signals encryption. There are different modes. We'll come to that. So we have insufficient replay prevention. What does it mean? We have a single byte which should help to prevent replay. If I capture 2 packets, so 2 messages actually, message 0, message 1, then I can just toggle between these messages and the receiver will just accept them. Let's have a look at the data which is sent. These are built on diff and fif information. So it's basically the diff is indicating what type of value is being sent, and the fif is more specified to is additionally specifying the unit. So the diff says, hey, this is a 4-byte value, and the fif then says, hey, this is a value which indicates wet hours, for example. Okay, I built a wireless sniffer on my own. There are commercial products actually available. I built one in Python, which is available from my JIT. So it helps to just sniff simple messages. I'm going to show it to you afterwards. Okay, unfortunately, vendors use seldom keys. They use stupid keys, for example, 1, 2, 3, 4, 5. You'll guess the rest. There are some they use FFFFFFF. And they have also proposed within the European norm to have at least 8 bytes different for each device. So we have a 16 bytes key, and they propose to have 8 bytes different. So the remaining 8 bytes will probably be the same. I know about vendors which use the same key for all their devices. Thousands and thousands of devices, the same key. What's the reason for that? They have a little handheld device which they use to manage those devices. And these are already rolled out, sold to the customer. And they're thinking that if they have a single key, it's easier to manage because they can just distribute that single key to those handhelds. Okay. Then I had a closer look to the protocol. We have different encryption modes actually. So there's DES, but there is AES 128 as well for the application layer encryption, and there is AES 128 for the extended link layer as well. So we have 2 bad modes actually, so I'm not going to use DES anymore. Then I thought, okay, let's have a look at the remaining 3 encryption algorithms. So are we safe with AES? AES is actually applied in CBC mode. CBC mode takes an IV, and that IV in that protocol is specified as to be 0. So, which means when we do some calculation, which means if I send a consumption value once, and in the second message, the same consumption value, then the decrypted packet will not change. So same plain text inputs will result in same ciphertext outputs. So what we could do with it is detect zero consumption. So we could detect whether someone is using energy or not. We know exactly when to rob the house and when not. Okay? They proposed actually to use a little date time type to prevent that, but the date time type granularity is minutes. Okay? And these devices are configured to send their messages within seconds, maybe 10 seconds, 20 seconds, 30 seconds. So that's sufficient to detect zero consumption, because over that minute, the packet ciphertext will not change. So you're still able to detect it. There are actually other types, type E and Y, which could be used for that purpose because they provide seconds actually. But nobody's using it. Good, then I thought, how about mode 5? It's a non-zero IV. So the IV is actually constructed from the frame header. So it's known information. So they take the manufacturer, the address of the device, and the access, so the message number, to create an IV. I then thought, okay, let's have a closer look at it. What could we do? We could still detect zero consumption. Why? If that device, I have a little example over here, it's just a simulator. It just sends meter values in a defined time. And it's configured to send its message every few seconds. Then you have to wait for 255 packets, and then you know whether energy was consumed or not, because it will be then the same IV, because the IV is constructed from the initial vector, the manufacturer, the address, and the access number. And the access number basically rolls over after 255. So be a bit patient and you will get to your maybe a nicer clock or whatever. Okay, then I thought let's have a look at the encryption mode 1 of the extended link layer. That's actually not CBC, it's counter mode. So counter mode means you take a number as an IV and then you just increment it over time, and you're going to encrypt it and XOR it with the plain text. If we have key stream repetition within a stream cipher, and counter mode is basically a stream cipher construction out of a block cipher. If we have that construct, then you should really avoid key stream repetition, because it allows you basically to recover some plain text. So you have two ciphertexts, you take them and you basically XOR them together, and you will get then a product which is equal to the XOR of the two plain texts. Okay? So let's say a meter is sending two consumption values. Once it's 341,000 watt hours, and once is sending 341 and 12 watt hours. The difference of that is actually 12, so it's 1 C in hex. So that difference is the same difference as you observe if you XOR the two ciphertexts you actually see. So you have the two ciphertexts which differ in 1 C at that point. What you then do is basically guess for possible values. So you guess for the possible highest difference and guess for the possible lowest difference. And you then get the highest difference is 28 and the lowest difference is 4. And because you know how the protocol is sending that consumption value, you know exactly at what position we are looking at, and we are looking at the last position of that consumption value. And we know then consumption must have changed between 4 and 28 watt hours. So if you observe a meter of a company, maybe a factory, then you probably get rid of your shares by the time they use less energy, and you buy shares by the time they have or they use more energy. You will know that before they publish their reports. Now the question is, do we get the key stream to repeat? I haven't answered that. For that purpose, we must have a look at the IV. So the IV in encryption mode 1 in the link layer is built from several components. Actually, the only one that differs is the time field. Okay. So to get the key stream to repeat, we need to be able to manipulate the time within the meter. And while looking at the IV is constructed of known values, so we can basically guess them before, it's predictable, and that lowers the whole security of that AES 128 encryption to 85 bits security. Still sufficient, but might change in time. Okay. So let's see whether we can manipulate the time. For that purpose, we need to have a look at the other protocol parts. There's special protocols for signaling alarms and errors. That's a special part of the protocol. It's not subject to encryption, so you can always get information from that. You know exactly what errors and alerts are being sent. You can send application resets, or you could do clock updates, which actually could be subject to encryption, but as you have heard, we could replay packets. So if we have captured a time update, then we just send the time update again, and the key stream is going to repeat. So, do we have some issues with message integrity because we saw confidentiality is totally broken? There are two mentioned actually on authentication within that standard, but it doesn't really propose a good way to do authentication, because the one thing that is proposed is totally broken, so nobody's actually using it. However, at the application layer, we do have CRCs, but that's it. There are no MACs, message authentication codes. A CRC could be manipulated easily. Yeah. There are actually signatures which are being proposed for encryption mode 5 and 6, but signatures are just proposed for the consumption value. So the idea is to have the consumption value signed, but actually no one is using it because law says if there will be a dispute, we're going to have a look at the display of the meter. That's it. So why should you then do an effort to implement consumption value signing? So there are no MACs, which means we can manipulate ciphertext and IVs. And I'm going to show you how we could manipulate that. So we're talking about CBC mode. So we are basically injecting a altered IV to that construct. So we need to alter the frame header for that purpose. And if we have a look, what we could basically alter is if we would change the manufacturer ID or the device address of the frame, then the packet would not be received correctly by the collector because the collector would not know what meter it actually sent. So we can't manipulate over there. We could try to manipulate the version and the type information. Some collectors use it to identify the meter. In that case, you can't manipulate there. Some don't. There you can. But this is pretty implementation dependent. And we do have the message number, which we can manipulate, but it actually destroys the trailing 2F. The 2F is the padding of the message. There are actually implementations which take care whether there is 2F at the end, and there are implementations which don't, because the structure of the data does basically tell the program how long the information is, and therefore there's no purpose to have a look what the remaining information, the 2F, is. So some take care of it, some don't. There's an interesting question. So if you have multiple meters using the same key, then you could manipulate actually part of the manufacturer ID and the device address. I would say normally you would have the same key on the same manufacturer devices, so you could only manipulate the device address, and you must then have exactly at that position you want to manipulate, there must be a meter which has the same address. So this is very unlikely, but it could be an option, a theoretical one. Okay, how could we manipulate that? So let's say we read a consumption value of 341 kilowatt hours from the meter. Let's calculate a fake consumption value for that. We take the plain text, the IV, and then we say, okay, we're going to manipulate the IV at that special position there. We flip bits to make it a 5 out of the 2, and this basically causes then during decryption that the consumption value will be less. So it will be 144.39 watt hours. I'm not only able to alter actually consumption values I receive, the same also accounts for commands collector send to meters. Exactly the same. So we do have another issue. There's partial encryption. So what does it mean? You can define a part of the protocol being encrypted. Let's say you're going to say, I have three blocks encrypted and the rest will be plain text. Now what you could do is just pick an encrypted packet and basically append your own plain text and alter the frame length, which is not encrypted as well. So let's say we have that value and it's encrypted, it looks like that. Then we just append our own value. So that's actually less consumption. Then it looks that way, and we have to alter the first byte, which indicates the frames grown, and send that to the collector. And actually some collectors accept that, some don't. And we found one which does. And I'm sure there are other ones which do as well. Okay. Let's have a look at the link layer. The link layer does also have no max in it. So it's just a cyclic redundancy check, but the cyclic redundancy check is encrypted, so it's hard to manipulate it. In that case, it's CC22. There's a tool, pretty cool one, Revenge, never heard of it before, but I stumbled over it, and you're able to calculate the cyclic redundancy check over wireless ambush packets, actually. And then I said, okay, let's have a look at the command. The command is 1 at the end. So let's turn on something. And what we would do is turn off something, okay? Let's make it a 0 and calculate the cyclic redundancy check again. So we have F147 for the cyclic redundancy check. Take that, so the on command, the off command, and we have the intercepted ciphertext as well. So I told you it's a stream cipher, so we can XOR it together. And what we finally do is we have that ciphertext, the manipulated one, which we actually send to the meter, which contains the off command. And that command actually has a proper CRC in it, because from that slide you see the first and the second byte changed. So ciphertext A and B differ in the first and the second byte and the last byte. So we have a bit flipping issue here. For the special protocol parts, for commands, network management, precision timing, clock synchronization, there doesn't exist any Mac. Okay, let's get to the demo. I quickly explain the setup. I have a fake meter over here. And that fake meter sends commands, which are being received by the collector and by my sniffer device. The sniffer device is actually a USB stick which features a Texas Instruments CC1101 chip, which is a transceiver, standard transceiver, and a piece of ARM code. So I have two actually of them. They have different firmware in it. One is configured as a sniffer and one is configured as a sender, because I have a sniffer tool, the wireless ambush sniffer tool, which is written in Google Go language. Actually, I didn't write it, so my apprentice did it, so he did a really cool job there. Thank you, Lucas. And I'm going to send the same packet again to the collector, or basically the sniffer device, because I have a fake collector over here, also written in software. Yeah, that's it. That tab is the sniffer. So it shows you what time the packet was received, what vendor actually the meter is, its meter ID, what type of meter it is. That one actually says it's a radio converter. Normally you would see there it's electricity meter or gas meter, heat meter. And you'll see the IV. And there are some buttons to replay and to do some attacks. So over here we have a fake collector. So that one is actually collecting the meter values of the fake meter. I'm gonna make it slightly bigger. So it states, hey, I have received information from a radio converter of that manufacturer. That's actually the key. And I got two values. I got a value which is, in that case, it's liters, for example. So it does just simulate a flow of liquid measured in liters. So that value does count up, and it does send just information as a string. So it's a test module. Okay. So then let's see whether it works. The tool is actually written with all nifty HTML5 features and WebSockets and all that stuff. Lucas is 18 years old, isn't this great? So here we go. First packet received. If you click on the packet, actually you see the bytes received, and we could use it. So I'm going to stop it. So it's not sending anything anymore. Okay. I take that packet, for example, and I replay it. You see, they get in. Okay. I'm going to show you that on the meter, on the collector. So we have received a value of 298. Now we receive a value of 300, 301, so we stop it. So it's a 301. Now I take an old packet So that one. It's 298 again. So I basically replayed an old packet which made the collector cause assuming, oh, it's a lower value. Okay, so that's energy fraud. I'm going to show you the extension attack as well. So you see there's a text Amber wireless test module. And that information is all encrypted. So it's all encrypted in here. And we just take one of these packets, go to the command pane. There's a feature called plain text extension. And I know about the structure of that protocol, of course. I know how a string does have to look like. I basically just append the information here. So we have, if we go to the collector, the string is defined here. So if you have a look at that string, the first byte actually tells, hey, that's variable data, so we don't know actually how long it is. Then that byte is going to tell it's a special type, and the 11 is going to tell, oh, this is a string. And then that byte is going to tell it's 20 bytes long. So we're going to skip that. And the 20. Okay, and we say, hi, Black Hat. It's actually low byte order, so I have to reverse it, and I want to have the hex part, so let's go. I put that over here, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bytes. Oh, is it B, right? Here we go, B. And then I would need to alter the first byte of the frame, you remember, but the tool does it on its own, so I don't have to care about that. Okay, I sent it. Thank you. Yeah. There's more the tool can, so there's a ping pong mode. So it basically takes 2 frames and sends it, it changes message 1, message 2, message 1, message 2. There's repeated replay, so you can send a message 1,000 times, for example, or a single replay. The tool is also available from the JIT. Let's go back to the slides. There are actually some issues with these attacks, because you saw I always disabled the meter. So because it would have been sending its real consumption values to the collector still. So you need to take account of that. So you somehow have to either shield the original meter, or you have to break it and then forward the information to the collector. Or what you could do as well is shield the meter and the receiver and then forward it. The advantage of that would be you can collect, for example, 100 meters within that shielded part, 100 packets within that shielded part. That's important because if you, for example, in Switzerland, if you use or if you have changes in your consumption behavior more than 20%, then your utility will figure it and they will roll a truck. Okay. So it would be good then to have maybe 100 packets and send them not in a short interval, but make the interval longer. So send them over days. then you steadily have some consumption still, but they're not going to figure there's something wrong. Okay? There's also another approach. So your meter is sending information, and you know exactly what the interval is. So it's a fixed interval. Every meter has a fixed interval within wireless ambers. So if you have a 10 seconds interval, then you will figure, okay, it's a 10 seconds. Then you will jam during that time and send your own packet. Jam, send packet. Make sure a sender device does not consume more energy than you're actually gaining. Huh? Okay. Good. How about the orchestrated blackout? I told you actually what I showed you is applicable to sending commands as well. So it's basically the same process. But we need to have maybe some devices nearby these houses to collect packets. So because we have maybe 100 meters of distance, or we have to war drive, then you get this information and you build a large sender somewhere in town, and you're going to send them. Okay. And it's going to be dark, so bring a flashlight. Okay, to sum it up, actually there's a company in Germany which is specializing in installations of wireless and wired M-Bus, and its company name brings it pretty much to the point. So we have key size, which is 64 bits, because they say only 8 bytes must be different. We have zero consumption detection, disclosure of consumption values. We have basically information on alerts, on tampering triggers which were triggered. We have information disclosure. I have not been telling you about the man-in-the-middle attack in routed environments because there is no authentication. We have also key disclosure there. There is a key distribution mechanism loosely specified within the norm, which allows for full key disclosure. So we could manipulate consumption values and also open and close valves or breakers. Actually, the German Federal Institute of Information Security has proposed an extension to the standard. It looks like it fixes part of what oh gosh, what's that? It fixes part of what I discovered. I get rid of all the wireless, so. And they also propose implementing TLS 1.2 on the protocol, but for me it seems it's maybe hard to implement TLS for a heat meter, for example. We'll see how it develops. There's actually no public analysis so far, but they look pretty robust. Yeah, my battery pack is empty. Thank you very much.